Everyone, we are back and we are going to do our basically this model to tune PID systems, the first of which being our Ziegler-Nichols ultimate sensitivity method. So this is a classical tuning method, especially predates a lot of the simulation tools. What we're going to do is we're going to set Ki and Kd to 0, so we're only going to use our P, proportional control, our gain. We're gradually going to increase until the basically the output is going to oscillate with constant amplitude. So basically we want to put our poles basically right here where we just have kind of the sine wave that just oscillates like so. Once we have this, we're going to call this gain at which we have this sustained oscillations. And again, we're not looking for something that's growing or changing or getting smaller. It needs to be sustained. We'll call that ultimate gain. The period of that oscillation, we have to calculate that. That's the ultimate period. Once we have those two things, we can define our Kp, our Ki, our Kd. This will then give us a really nice stable system. So we're going to push our system to the edge of instability by making it marginally stable, putting the poles basically right here, and then we'll figure out, then we can find essentially our tunable parameters. We're going to assume essentially this response function. Here's our plant. This is our controller, but remember we're setting this is to 0 initially, and so we're just increasing this. So let's go ahead and get to it. So we're going to go ahead. I'm going to close out this. I'm going to go to my Ziegler-Nichols, and we're going to go through and shift-enter everything. Complex. Now that looks a lot nicer. We can kind of see what our system looks like. Our new transfer function. Once we set this here, we can get our Laplace transform. And now we can start to play essentially with this system and start to tune it, right? So let's go ahead and let's put it right here. So remember, we want it marginally stable, meaning we want some poles to be on that imaginary axis. So as a first step, I think it's always good to look at where those poles are lying. So nothing yet, nothing yet, nothing yet. We're pushing it, and now, so like 180, let's push it a little bit. Like 180, 190, like, yeah, let's say like 190, or 188. Let's look at kind of our system response. So let's go ahead, let's say 180, 188. If we put that Kp value. It's oscillatory, but it's not kind of like the same amplitude, right? So let's keep increasing. 190. Looking better. But we can kind of see it's a little bit dying off. But again, it's not a huge deal, but it's a little bit. What if we go right to 192? Let's see what this looks like. And we can also look at the poles too. This looks good. At least to me, I think that they're all the same height, right? 1.74, 1.74, 1.73, you know. This looks pretty good. So we need to calculate the period, so you can just do 0.71, 2.02. We can look at the difference. So this would be our ultimate gain, 192. The period, our ultimate period is this. So our ultimate gain would be 192. These would be our new Kp, Ki, Kd as a function of ultimate gain and our ultimate period. So those would be the parameters. So we can set that in here. Our new system looks like so. Are we stable? Yes, we are indeed. And then we can look at that system response. And look at that. Really nice, right? Responds, minimal vibrations, and then we reach that steady state. Fantastic. So that is our Ziegler-Nichols ultimate sensitivity method. There's an additional method, the quarter decay method. It's a modified Ziegler-Nichols approach. Oftentimes, you can't basically produce sustained oscillations in a system. When you have a system that behaves like that, you can use essentially this quarter decay approach. Same starting point. Set this to 0, set this to 0. Slowly increase this until we get underdamped oscillations that will decay over time. And we're going to increase that Kp value into the ratio of the second peak to the first peak is approximately a quarter. And make sure we're looking at the peak amplitude and we're subtracting essentially the peak height from steady state value. And we're going to see that in just a second. Once we have that, you define your ultimate gain again. You have to calculate that ultimate period, and then you're going to have some similar definitions for, actually the exact same definitions to determine the values or initial tuning values, right? Like these are initial, it's not the perfect response, but it's a good starting point where you can fine tune. So let's do quarter decay, and let's just do it with the same system. So we're going to set this up again, our new function. And what we need to do now is that quarter decay approach. So let's go ahead and let's start it at 70. So the first thing that we may need is, what's our steady state value at your steady state, or at your particular KP, right? So I need to take the ratio, right, of the height of the second peak, which 0.9, right? 0.9 over the ratio of the first peak. Now you see I'm subtracting there, so the height of this peak 1.18, 1.17, and you see I'm subtracting each of these by 0.82. So 0.22, pretty good, but let's increase it a little bit. Let's go to 75 and 0.83. When we get 75, we can calculate it, and we can look and see. So for example, now we're 1.121, and then 0.93. So if I do, for example, 0.93 minus 0.83 divided by, what is it, 1.21 minus 0.83, we're pretty close. So 0.25, 0.26, again, we can kind of tune that, but this looks good for a starting point. We calculate essentially the period, again, between essentially those, between the peaks. So you can kind of see here and here, the first peak and the second peak of the oscillations. It'll be twice, the ultimate gain now is twice that value, and then other than that, we know how to do here, here, and here. And we can see the response of our system. Poles, we are indeed stable, and then less of an overshoot, right? Fewer oscillations. It's a nice, smooth response function. So there you go. That's it. So that is your kind of controls lecture for PID controls. Next time, we are going to get into lecture 12, and we're almost at the end of our journey, sadly. But there's a long lecture ahead of us. Root locus. Root locus is incredibly important. It's another tool for stability analysis, and we will see you all in that next video. So, and especially basically how they behave in terms of your gain. So, or your controller. So we'll see you next time. Thanks.